Chapter 10, Section 7. We're going to talk about the distance formula, midpoint formula, and other applications, which are basically going to give us some gateways to take a lot of these algebra tools we've been going through and apply them to geometry and in a couple different ways. But first, really, the first part of this is about geometry, and the first one with right triangles is the Pythagorean theorem. And just to review what a right triangle is, again, we have a triangle with a right angle or 90-degree angle. It's shown here with that arc marking 90 degrees, but we'll see this square symbol. We'll make a square looking thing in the right angle portion of that, which indicates a right angle. We have a lot of things that end up with right angles, so they have some symbols for it. Well, Pythagorean found out a long time ago that if you took any right triangle and took the legs of the right angle and squared them and added them together, you'd always get the square of the hypotenuse. A hypotenuse is the longest side of a right triangle, but it's also the one opposite the biggest angle, which is the 90-degree angle. So both of these, all the angles of of any triangle, add up to 180 degrees. So if this is 90, this angle and this angle have to add up to 90 degrees. So they're definitely smaller than that. But this is a very handy relationship that occurs with these types of triangles. So if I know two lengths of legs or hypotenuse, any two of those side lengths, I can use this to figure out what that third one is. And they're also going to talk about square roots again, a little bit about non-negative real number n. If we have x squared is equal to n, then x is equal to square root of n, or x is equal to the opposite of that, or a negative square root of n. And they go right into an application, which is kind of nice. We get to see where it's applied to right away. In this example with baseball, a baseball diamond is a square with sides of a length of 90 feet. So from home base to first base is 90, to second base is another 90, 90, 90. The only way that can occur to have all equal sides is this has to square. So these are all 90-degree angles here formed in this square, really, which is important here when we're going to deal with the building of this next triangle. Well, suppose a catcher fields a ball while standing on the third baseline 10 feet from home plate, as shown in this figure. How far is the catcher's throw to first base? They're going to ask us to give the exact answer in an approximate to 3 decimal places. Well, the solution is to draw a picture, and almost always in any kind of math deal, if you can draw a picture, draw a picture. And the goal would be in this case that we're looking for where's this right triangle going to occur and what are the sides to this, and what are we dealing with. So they draw this picture here. Well, we know it's 90 feet to first base. We know that the catcher is right on third baseline, and he's 10 feet away from home base. So here are two legs of that right triangle. And what are they asking for? Is this distance that the catcher throws to first base? Well, here are the legs of a right triangle. We're looking for the hypotenuse of this right triangle. So we can fill in the parts here into Pythagorean's theorem, and the distance squared that we're looking for is going to equal the one leg squared plus the other leg squared. And so we get 8,200, 8,200. Well, to find out what d is, we would take the square root of both sides, and we're going to have two answers really right away. As we take square root of both sides, we get, which will be the square root of 8,200 and the negative square root of 8,200. Now, when you think about the application that we're dealing with, we're probably only interested in the positive value. We're not talking, there's no negative distance is going to occur in this real world situation. So the exact answer again is to simplify this radical, this square root, which you could do through prime factorization, or you might recognize that this is 82 times 100, and 100 is a perfect square. The square root of 100 is 10, and we get 10 times the square root of 82. Now I would probably factor 82 to make sure I don't have a 4 factor or a 16 factor or something like that, or things that are even, they have to be even in this case. Okay. Well, there aren't any other perfect squares in factoring of that, so this is the exact answer. The approximate answer to 3 decimal places. So if you took on your calculator and just went square root of 8200, enter, you're going to get a decimal, which would be 90.554 or something else would go on there. Something smaller than 5 next to that 4, or it would round up. And that's what they asked for, is exact answer and going to 3 decimal places, which is probably way more than the amount of accuracy we need in this case. So basically he threw just a little bit over a half of a foot farther than if he stood at home plate and threw to first base. That's 90 feet. By moving over 10 feet, added about a little more than half of a foot or 6 inches to that throw. Now guy line wires, these here end up with, and hopefully they've installed that pole in the right way, and so it's not leaning, because it'll be a lot more stable. They're looking at here, and this is a base of a 40-foot long guy wire is 15 feet from the telephone pole that it anchors. How high up the pole does a guy line reach? Okay, and so give the exact answer and approximate again here to 3 decimal places. Well, let's make a drawing of this thing so we can draw in the triangle. And what they're looking for here again is they know that this wire is 40 feet and that this is 15 feet from the pole is where it's anchored onto the ground. They want to know what's the height of the pole to the guy line attachment to the pole, not the entire pole. So what we have here is H is a leg, and 15 is a leg, and 40 is a hypotenuse. So we fill that into Pythagorean's theorem, and we'd end up with H squared plus 15 squared equals 40 squared. Leg squared plus leg squared equals hypotenuse squared. We end up with these numbers. Solve for H squared. We get H squared equals 1375. So H is equal to the square root of 1375. Now what they do find out is this is a multiple of 25. You might be able to recognize that with the last 2 digits being some increment of 25 added, and you could see that right away, or you could prime factor and find out your perfect squares. So again, it's a distance issue, real distance, so we're dealing with the positive value, and then we simplify this square root and keep it accurate, and it's 5 square roots of 55, and then the approximate is 37.018, or excuse me, 081. Okay, so 2 applications of Pythagorean's theorem. This next thing they're going to talk about is really some shortcuts that have been created because of what we know about a lot of geometry that occurs, those kinds of things. I'm going to throw some stuff in here that's from geometry, but these special triangles we're going to go through really can save a lot of time because they're going to set up a consistent relationship between the sides. This first one we're looking at is something called an isosceles right triangle. Isosceles means that 2 of the sides of the triangle are equal. And there's also another thing. The only way that can occur in a triangle is that these angles opposite the equal sides have to be equal too. Well, if this is 90 degrees and these two have to add up to another 90 to make that 180 degrees, the only way that can occur is that they have to be half of 90, which is 45. Okay? So you start recognizing, hey, this is a special triangle. When I see a 90 and a 45 degree angle, I know the other one has to be 45. I have an isosceles triangle. Well, they're going through the process of how they discovered some things that were shortcuts that we can find with Pythagorean's theorem. Well, in this case, if I use Pythagorean's theorem, I have A and A are the sides, right? So they fill in the legs of the right angle are A squared plus B squared, right, in the Pythagorean's theorem. Well, in this special case, they're the same, so it's A squared plus A squared. So you end up with 2A squared. So C, the hypotenuse, this would be C squared equals 2A squared. Well, then C would have to be the square root of 2A squared. Well, if I simplify that, I end up with the square root of A squared is A, and the square root of 2. So A square root's of 2. Well, we can apply this in a lot of different ways, and they're going to give us a couple examples. One leg of the isosceles triangle measures 7 centimeters. We can find the length of the hypotenuse, give the exact answer, and then this approximation to 3 decimal places again. Well, let's look at this. So 7 here. Well, what's this one going to be? If it's isosceles, this is 7, right? Now we could do the whole Pythagorean's theorem or apply this special relationship that we found out. Well, if I know what A is, this is like a formula for finding C, the hypotenuse. I fill in the number for A, and I got the hypotenuse. So in this case, A is 7, so the hypotenuse C, in this case C, is 7 square roots of 2. Well, that's the exact answer, and then I could take 7 times the square root of 2 on your calculator, and you're going to get approximately 9.899, something smaller than 5, right? And, so make sure you answer the question the way they wanted their responses or their answer to this. Let's look at this next one here. It says a hypotenuse of an isosceles triangle is 5 feet long. Find the length of a leg. Give the exact and then approximate again. Well, we replace C with 5, right? So 5 will equal this A times the square root of 2. Well, how do you solve for A? Well, we take 1 over the square root of 2 times both sides, or they say dividing. So I end up with 5 square roots of 2, 5 over the square root of 2. Well, we rationalize that denominator, which is usually a pretty standard method. In the prior lesson we were rationalizing denominators, or making sure the denominator is a rational number. It doesn't have a radical symbol in any way, or a fractional exponent. Well, we do that again. They don't go through this. Would be, well, I'd take this fraction right here times 1, and that 1 I would multiply by would be the square root of 2 over the square root of 2. So we end up with 5 square roots of 2 over 2 equals A. Okay. Now, they actually take it both ways. Usually when we're working with fractions and irrational numbers, most places I've seen they would prefer that it be this way. And then the approximate would be, you could take either one of these and take 5 and divide it by the square root of 2, or take 5 times square root of 2 and divide by 2, and you'll get 3.536. Okay? So here's that relationship. They give us a box here. The lengths within an isosceles right triangle, the length of the hypotenuse in an isosceles right triangle, or a 45-45-90 triangle, is the length of the leg times 2, or C equals A square roots of 2. Now here's another special triangle. which is a 30, 60, 90 deal. And let's start with a equilateral triangle. Right here, this whole triangle is equilateral, and to have equilateral, equal means equals means equal, right? And lateral means side. So equilateral is equal-sided triangle. And also what occurs is you end up with equal opposite angles, right? So you end up, the only way that can occur is that all these have to add up to 180, so you have 60, 60, and 60. Well, this is an equilateral triangle, and this is not a right triangle at all, but what if we split this into two right triangles? And the only way that can happen is you have the height from this point, and that's why they call it a height. It's like the highest point on this triangle down at a right angle to the other opposite side of that angle. And what happens when you do that, it's going to create a 90-degree angle. Well, now I know I have a 90 and a 60, so what does this one have to be? Well, I only have 30 left to make that 180. Here's 60, 90, and 30. So this splits this angle into two equal parts too. So we end up with two 30, 60, 90 triangles. Now they start filling in some information here. They're saying, well, if this side, now we got this ABC kind of thing going on. If this side is A, and A, what is the length of the whole side of my original triangle? Well, this is split in half, so A and A, well, this is 2A all along here. And that's where they get this 2A on this hypotenuse. In fact, all these would be 2A, 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 right? Well, when I split this, I have these two triangles. I have this half, right, or A and half A. Well, the hypotenuse of these two 30, 60, 90 triangles is 2A. Well, here's Pythagorean's theorem again. I have a right triangle. I know one side and I know the hypotenuse. We want to find out what's this thing with, what's a relationship that A has with the other leg. So they put this in and they say, well, I have A squared plus B squared, that was Pythagorean's theorem, right, equals C squared. But we've already determined, if we think about, that we started with this equilateral triangle, then this hypotenuse has to be 2A. So we can put in here and say C is really 2A, so it's 2A to the 2 power here. They actually perform that squaring, or that to the 2 power, you get A squared plus B squared equals 4A squared. B squared, they add a negative A squared to both sides, and end up with B squared equals 3A squared B. They take the square root of B squared, you get B equals the square root of 3A squared. You can simplify that radical to be A times the square root of 3. And then it says here, this relationship is worth remembering. Yes, it can save a lot of time rather than having to go through this Pythagorean theorem and remember a lot of things about geometry. We can use this relationship to solve a lot of problems, because this is a triangle that occurs a lot too. So in example 5, the shorter leg of a 30, 60, 90 degree triangle measures 8 inches. Find the lengths of the other sides. Well, if I know one side now, because of this special relationship we had of this special triangle, I can say, well, if this is A, then I know the hypotenuse is 2 times that A, this 2A, where they got that, right? So I can fill that in as 16. And then the other leg is A times the square root of 3, or this one is going to be 8 square roots of 3. And that's what they're asking you to find. It says find the lengths of the other sides. Well, we know C is exactly 16 and B is exactly 8 square roots of 3. And then if we wanted an approximation for this, you take it to 3 decimal places, where there is no need to approximate a value for C because we have a rational exact answer. Okay, example 6 is going to take a different leg of this 30, 60, 90 and do that. Very, very critical to draw the pictures and to figure out what parts we're talking about here. In this case, the length of this longer leg, the longer leg is the one opposite the 60-degree angle, and the shorter leg is the smaller angle, 30 degree. So we're talking about this leg right here is 14 centimeters. So they give us this one is 14 centimeters and we don't know the short leg or the hypotenuse. Well, we do know this relationship that 14 is equal to a times the square root of 3. So then I can solve for a and I get 14 square roots of 3. Okay? And now if I know what a is, I take 2 times it and I get the hypotenuse. So they take 2 times that and they get 28 square roots of 3. And that's really all there is to it. And then we can rationalize the denominator like they do here, or just leave it as 28 over the square root of 3 centimeters. And the approximate would be, on your calculator, go 28 divided by square root of 3, and you'll get this. So pretty handy deal with these three triangles. And here's that relationship drawn out, put in a box to say here it's almost like a rule or a law. But really what they're doing is they found shortcuts again off of Pythagorean's theorem with these special triangles. But very, very handy and cuts a lot of steps out of doing some of these problems, which is a very good strategy for making less errors. Now the distance formula is probably one of the biggest things, and we're gonna start taking the geometry and working with a coordinate plane. And you know, we can draw two-dimensional figures on a coordinate plane and then deal with the ordered pairs, and it's going to bring up some stuff about that we've covered before in geometry. And it's going to say, hey, we're going to use this Pythagorean's theorem to get the distance between any 2 points on a coordinate plane. And they're going to review us some things like here. If I have a one-dimension thing where I have a number line, there's only x values, there's no y's, you know, there's no ordered pairs. If I want to get the distance between these 2 points, I take the absolute value of their difference. So I would take 4 minus a negative 3, which is 7, and the absolute value of that is 7, okay, distance from 0. Well, if I went the other way, if I went negative 3 minus negative 4, I end up with negative 7. The absolute value gives me that same thing. So this is really the distance formula between any 2 points on a number line, right? Is the absolute value of their difference. So we can apply this to ordered pairs too, and they're going to give us this exploring concepts where the coordinates for point A in this case are negative or 4, negative 4. Remember, the first coordinate is the horizontal, which is like horizon. You know, when you look at a sunset, that you're looking at the horizon, that is a line that goes this way in a sense. And the second number is always the vertical up and down movement. So just to remind you, and there's rules about that, just so when somebody writes this ordered pair, we all graph it in the same place right here. Okay. To find the distance from point 1, 2, the ordered pair 1, 2, to A, so they're looking for this distance right here. We can use the Pythagorean theorem, because what I have here, I can make a right triangle that I know the distances of the legs from this point to this point, based on that two-dimensional thing here too, is I have a straight line, and I can say, well, this is 2 in this deal, and down here is negative 4. So I know that the distance between this point and this point A that I created a right triangle with, or this longer leg of this right triangle, is 2 minus -4 or 6. The distance between this point and this point is, well, it's at 1 here is that position, and over here it's at 4, so 1 minus 4, which is 3. Okay, that's what they're telling us here, they're answering those questions. Well, now I have two legs of this right triangle. I can find out what the hypotenuse is, or the distance between these 2 points, which would be 3 squared plus 6 squared, which ends up to be 45, and which is 9 times 5, which we can simplify to be, when we take the square root of 45, is 3 square roots of 5. Now we can generalize this. They can say, well, what if does this work, or how can we set this up for all points? Now they bring in this notation, or way to deal with trying to represent in the best way so you can remember what these ordered pairs mean. So like this point right here, they say is x sub 1, y sub 1. In other words, an x coordinate, y coordinate here, and it's going to be for point 1. So they call a little sub there saying, what is the ordered pairs from? Well, it's this point 1. Where this one is, the x coordinate is different. It's a different sub, right? And it's for point 2. But y sub 1, there's no change vertically from this point to this point. So it's going to have the same y coordinate here. And then on this one, it's going to have a different x coordinate, which is basically the same as this one. And the y coordinate is going to be different. It's not the same as this one because there's a vertical distance that did occur. Well, then they say, well, if I took the distance between this point and this point, it only involves the y coordinates here, doesn't it? Because the x coordinates are the same. It's like the distance on a straight line, or just on a number line. Well, it's going to be this y coordinate minus the other one, and you take the absolute value. That'll always give you the distance between these 2 points on a line. Same here, we have a change that occurs in the x coordinates, so that's really all that matters, because there's no vertical change between this point and this point. So we can get, basically, with the absolute value of x squared minus x1, I get the distance of this line right here. Okay, so now I have 2 legs of a right triangle. So that's where they come out. They say, well, using the Pythagorean theorem, I'd square this absolute value, which is the distance right here, this distance, and then I square this absolute value, which is this distance right here, and that should add up to the hypotenuse squared, this distance that we're looking for squared. Since the square of the number is the same in the opposite sides, we can replace the absolute value signs with parentheses. In other words, because of this, what happens when you square things, almost the absolute value is a redundancy in a sense. It's always going to come out with a positive value. So they just say, well, let's just put parentheses there and not have to deal with the absolute value. So taking the principle of square root, we found this formula, which is, well, to find d, I have to take the square root of d. So I have to take the square root of this entire side, and they get this formula. And it is basically used as a formula, and I think it would be a very good idea to remember this formula. So if I know the coordinates of these 2 points and I want to find the distance between those two, I take the x coordinate from the second point minus the x coordinate of the y first point and square that, right? And then I'm going to add it to the y coordinate of the second point minus the first point y coordinate, and then square that. Add those together, take the square root. Now you have to, and why they do all this thing with subs is that subtraction order does matter. Commutative property doesn't work with subtraction. So if you start with the second point, x and y, x coordinate, you have to use the second point y coordinate as your first part of your subtraction. Okay. So to find the distance between these 2 points, 5 and -1, and the point -4, 6, they put it in the formula. They took -4 from the second point here, that's the x coordinate, minus this x coordinate at 5, and then they put the y coordinate, again this because they started with this point, this y coordinate goes in first, minus the y coordinate of the second point, which is -1. And they end up with -9 squared plus 7 squared, or the square root of 130, which is, there's no perfect squares to simplify, and the approximate value is 11.402. So that's an application of the distance formula. You could write all this out. You could make the right triangle and go through Pythagorean's theorem, or you can shortcut right to this distance formula. Another formula is the midpoint formula, and we're not going to go through the whole proof on that, but it is basically you add up the x coordinates and divide by 2, and add up the y coordinates of the 2 points and divide by 2, and that will give you the midpoint of this line segment that goes between these 2 points that we're talking about. So to find the midpoint of a segment with the endpoints of -2, 3 and 4, -6, is I add the x coordinates, which are -2 and 4, add those together and divide by 2, and then the other one is 3 plus -6, so you end up with 2 over 2, or 1 as the x coordinate and -3 halves as y coordinate. If I plot that point, it will end up right in the midpoint of that line segment. That's what they're looking for. And that's it for section 7.